All right. So, chapter 9 is a kind of interesting one. It's a, it's a big U-turn from all the calculations we've been doing. Okay, so not as many calculations here anymore. But we're going to go into a lot more detail about how it is that how it is that a lot of the things behave the way that they do. We did a lot, we've dealt with charges a whole lot, all the plus ones and minus ones and stuff like that. But we sort of learned it just as a pattern from the periodic table. In this chapter, we'll be able to figure out actually why it is that that's the case, why certain arrangements of electrons are more stable than others. Okay? So, and it relates to chemical properties. Why is hydrogen explosive but noble gases are unreactive? Right? The Hindenburg exploded when there was a fire, but blimps now are filled with helium that would put out fires. Okay? Why do elements within one group tend to form similar ions? Right? FCl, they all form 1 minus ions, but why is that? So it's due to the behavior of the electrons in those atoms, and that's what this chapter is about. So we're going to talk all about electrons and their really unusual behaviors and their positions in the atoms and stuff like that. The issue is that electrons, we talked about electrons before. Remember what an atom looks like. We've got a nucleus that has protons and neutrons, and then surrounding that nucleus are electrons. They're all flying around, okay, going kind of in all directions. And almost all of an atom's mass comes from the nucleus, the protons and the neutrons. Electrons are almost massless. They do have a mass, but it's insignificant in the total mass of an atom. Okay? So they're nearly massless. They're much smaller than an atom. How is it that we know anything about them at all? It gives us an opportunity, actually, to tell a nice story about indirect observation. It's actually only recently that we can actually see atoms. They just kind of look like fuzzy balls under an electron microscope, just kind of a fluffy sphere. Okay? But it's the electrons inside that atom that give it chemical properties, that make it do chemical reactions, that make ionic and covalent bonding, which we'll be talking about later. All of that came about by studying light. So we're into the 1900s now. All of our chemistry, well, all of our discoveries and stuff had been sort of in the late 1800s, maybe early 1900s. But in the 1910s and 20s and so on, that's when chemistry and physics were really taking off, and we really started to get a mature understanding of what's going on inside of the atom, especially with electrons. But it all came from studying light, because as we'll see, light and electrons have quite a bit in common. So that's where it sort of comes from. Light is one way of describing electromagnetic radiation, but it would be a little bit more disturbing to the general public if we called it an electromagnetic radiation bulb instead of a light bulb or something like that, but that's what it is. But all it is a type of energy that travels in waves. We're going to talk about those waves, and travels at a constant speed of 3 times 10 to the 8 meters per second. So think of 1 second, 3 times 10 to the 8 meters. That's roughly the distance from the Earth to the moon. Okay? So if you think of a flashlight or a laser or something like that shining towards the moon, it will take 1 second around for it to get from the surface of the Earth to the surface of the moon. Okay? So it's instantaneous to our perceptions. It becomes annoyingly slow to astronomers and cosmologists that are studying stars that are in different galaxies and things like that. But it's actually a really interesting experiment if you haven't heard about it. The first astronauts that walked on the moon, or I don't know if it was actually one. It was one of the first lunar landing missions. What they did is they placed a series of reflectors on the surface of the moon, and they're retroreflectors, so they'll reflect light right back in the same direction it came from. So that allows us to do a really interesting experiment. There's an observatory in Hawaii that is set up to do this one experiment where it fires a laser at the moon, aimed right towards those mirrors, those reflectors, and then it has a detector that times how long it takes for that light to make its way back to the Earth. So we're able to get a very, very accurate measurement of, well, however you want to do it, either the speed of light or the distance of the Earth to the moon. But it sort of fires pulses, but the way you can think of it is they fire a pulse, okay? And you see a little graph, it fires a pulse, and then 2 seconds later, you see it detecting the pulse coming right back. So I think that's one of the best pieces of evidence for all the lunar landing doubters out there. That the only way that would work is that if somebody literally put a mirror on the moon. They could, with that measurement, they could measure the distance from the Earth to the moon very, very accurately. So I'm sure they would be able to track that over time. Yeah, absolutely. So, all right. So let's talk about what light is made of and how we perceive light. Because one of the big ways that we perceive light is its color. Okay? But color itself is not a property of light. Color is what our brain uses to tell different wavelengths of light apart. Okay? Remember we said that light travels in waves. Okay? So these are just sort of waves of energy. The wavelength, that's a, let me show you that. That is a Greek lambda, lowercase lambda. Okay? Looks like that. That's just a symbol for wavelength, and that's just the distance from the peak of one wave to the next wave, right, to the peak of the next wave. Okay? So, if we look at red light versus blue light, their wavelength is different. Red light, on average, would have a wavelength of around 750 nm. What does that N stand for? Anybody remember that prefix? That's nano. If you've heard of like nanotechnology or nanobots or something like that, that's referring to this range of length in meters. So nano is 10 to the minus 9. So 750 nanometers, that's 750 times 10 to the minus 9 meters. In proper scientific, we'd have to move the decimal point. We'd get 7.5. 10 to the minus 7. Okay? So that's the scale that we're operating on. So that's a meter. That's a tenth of a meter. Right? Centimeter is 1/100th. So that's 10 to the minus 2. Millimeter, 10 to the minus 3. Okay? Thickness of hairs, that's 10 to the minus 5 or 6, something like that. Okay? So 10 to the minus 7, it's getting into 1/100th or so of the width of a human hair. So small, okay, but not as small as atoms. Atoms are like 10 to the minus 10, something like that. Okay? So somewhere between an atom and the width of a human hair. That's the width of these waves of visible light. Okay? But blue light has a shorter wavelength. Okay, it's centered around 450 nanometers. And I drew these waves as colored, but the light waves themselves are not red or blue. Okay? All a light wave is a wave of energy with a certain wavelength. And it reacts with the cones in our eyes, sends a signal to your brain, and your brain has invented colors as a way to tell different wavelengths apart. Okay? So color exists nowhere except inside of your brain. That's an interesting thing to think about. But your eyes are just sensors that detect different wavelengths and different combinations. Your brain has totally invented color as its way of interpreting that. So kind of interesting to think about. But that's what is different about different colors of light, and that's going to be important for us in a little bit. Okay? Anybody that's a Pink Floyd fan has seen a picture like that. That would be a light source. It has to be incandescent for this to work. All right? In other words, it has a glowing filament in it. When I started teaching, I didn't have to say that. It was just a light bulb. But an incandescent light bulb has a glowing filament in it that actually gives off a combination of pretty much all wavelengths of visible light. So when it's passed through a prism, it separates them out by their wavelength so that you can see the individual colors that make it up. And what you would end up with is a smooth, continuous spectrum A spectrum is just being able to see all the wavelengths of a certain sample of light. That's a spectrum. Okay? So you would see a smooth, continuous wavelength going all the way through the rainbow, but you'd see essentially an infinite number of individual colors. Okay? They wouldn't be really separated out. It would be totally smooth, going from red with the longest wavelength through violet with the shortest wavelength. And the reason it separates out is really because of the wavelength. When light passes from one substance to another, it bounces amongst the particles at different speeds. So when it's at an angle like that, that means the shorter wavelengths, that's right, shorter wavelengths, bend at a more extreme angle than the longer wavelengths. See how that works? If this was the original angle, do that a little better. Notice how red here, it's got an angle of refraction, it's called, about like that. The violet, though, bent at a much more extreme angle because of its shorter wavelength. So it sort of separates things out by their wavelength like that. The shorter wavelengths get bent at a more extreme angle than the longer wavelengths, and that's why you can separate them. When you see a rainbow, you're seeing the exact same thing happen, but it's the suspended water droplets in the air that are acting as prisms. So it actually works when the sun is at your back, and it shines through the water droplets and reflects backwards towards you. And so next time you see a rainbow, always, as you're looking at a rainbow, the sun will always be at your back because the light bounces through the water droplets and back towards you. It's kind of interesting how that works. Okay, so, but again, this is going to be important to us, that prisms separate out the individual wavelengths of light. That's how they actually discovered something. But visible light, what we call light, or visible light, is just one small portion of all of electromagnetic radiation. Okay? This whole thing is the electromagnetic spectrum. You've probably seen something like that before. But visible light is just the particular range of electromagnetic radiation that our eyes can react to. Okay? That's it. So it's just this one tiny little segment right here that our eyes happen to be sensitive to. Let's look at how this is sort of arranged here. So these are wavelengths, okay, in meters, and it's just sort of the power of 10. So I told you visible light was on the 10 to the minus 7 range. Okay? Starting way over at this end, okay, these are the longest wavelength, okay, when we're in radio waves. Okay? And over here, shortest wavelength, 10 to the minus 15. So that's getting smaller than atoms themselves, right? The size of atoms themselves are in here somewhere. Okay? 10, maybe 9, so somewhere in there. So we've gone from smaller to an atom. Here's a meter. Right, here's 10, 100, 1,000 meters, 10,000 meters, 100,000 meters. Okay? So we're approaching the size of a planet when we're getting much further out over here. So that's our scale that we're dealing with. Okay? Also, then take a look at what happens to energy. Where we had the longest wavelength, those ones had the lowest energy. And the shortest wavelengths, those ones had the highest energy. So energy and wavelength, they don't change together, right? They don't go the same direction. They're sort of opposites. Anybody know what that's called, what that relationship is called, whereas one thing increases, the other thing decreases? Inverse? Yeah, they are inversely proportional. Okay. So that's important to us as well. The reason for that is because, remember, all of these are traveling at a fixed speed. Okay? They're all traveling at the speed of light, which is a universal constant. So if we've got a huge, long wavelength, and it's traveling at a fixed speed, we have very few of those complete waves passing through any point in a given time. Okay? Whereas if you have a very short wavelength, traveling at the same speed, you'll have a lot of those waves traveling through any point. Okay? So in mastering chemistry, you're going to see a little bit about frequency. Okay? Frequency is just how many waves pass in a certain amount of time. Okay? So high frequency. Okay. So lots of waves per second, okay, versus fewer waves per second. Okay. So you just think of that. If you have a long wave, it takes a long time for you to get one complete wave through any point. Okay. So frequency and energy are related. Okay? So if you've got low frequency, you have fewer of those waves passing through a point, and that imparts less energy. If you've got high frequency, lots and lots of those waves passing through a point, that can transfer more energy that way. Does that make sense? So energy and wavelength are inversely proportional. Okay? That's important. So let's go through this. Let's start with the lowest energy waves, radio waves. It's called radio waves, but any kind of electronic transmission through the air uses radio waves. So radio and TV and cell phone signals and anything like that. Okay? So radio waves have the longest wavelength, the lowest energy. Okay. And there's tremendous amount of physics to radio waves. If you ever know anybody that is a ham radio operator, they had to take a whole course on the physics of radio waves and why different frequencies have different properties. Some of them can, the ones that have just the right wavelength are able to bounce off certain parts of the atmosphere and come back down so that you can have really long distance communication almost across the world with certain wavelengths of radio waves. The difference between AM and FM radio has to do with the difference in their wavelengths. AM is very long wavelengths and FM is shorter wavelengths. So that affects how they travel around obstacles. Really long wavelengths can go around buildings and trees and hills and stuff like that, but shorter wavelengths get blocked by obstacles. So microwaves are interesting because that's how you heat up your coffee, right? The way that works is that the energy in microwaves is just right to vibrate water molecules. So to get something moving or vibrating back and forth, it has to be hit at sort of just the right time. Think of pushing a swing. You have to be pushing at just the right time for that to work. Okay? If you try to push when the person is over on the other side, it's not going to work. So microwaves have just the right frequency so that as water molecules start moving, they're pushing those water molecules just at the right time. Okay? So that's why microwaves will heat up water, but will not heat up just like paper or something like that, or if something is totally dry, the microwave won't work well. Okay? It's really just getting the water molecules moving faster, which is a higher temperature. Okay? Infrared, just like visible, say that, has pretty much all the properties of visible light, except it's outside of the range that our eyes react to. Okay? So I usually have one here. Your remote control has a little LED on the end of it. When you push a button, that's blinking infrared light, but you can't see it because your eyes don't see infrared. Okay? And on the TV or whatever, there's just a detector that's looking for that particular wavelength of light that's blinking away. Okay? The other thing infrared is used for is certain types of night vision. So the kind of green night vision goggles, that just amplifies regular light. But you can do night vision with heat too, or if you have, there are thermal imaging cameras that can do that. So this picture came from, because remember after the Boston bombing, when the guy was running and hiding through those neighborhoods, they found him hiding under the cover of a boat in somebody's backyard, and it was a thermal imaging camera. This is the actual picture of it. You can see his outline there in black because he's warmer than the surroundings. So even under the tarp there, they were able to see the heat that he was giving off. Sort of blew his cover a little bit. But the way that works is that everything that has any kind of temperature is emitting electromagnetic radiation. It's just that it has to be a really high temperature for it to give off visible light. Think of like heating up some metal in a fire or something like that. Eventually it'll get hot enough so that it glows. Okay? It has to get really hot to emit visible light. But things that are just room temperature are emitting infrared light. Okay? You are all emitting infrared light right now, okay? Just because you have some temperature. I hope none of you are emitting visible light. So a camera that can detect infrared light can see the different wavelengths that it's giving off and can use that to estimate temperatures. So it's pretty neat. Visible, what we can see. UV, and of course the reason it's infrared and ultraviolet is because they're on either side of red and violet of the visible spectrum, right? Infrared is just past red, okay, so just longer wavelengths than red. Ultraviolet is just shorter wavelengths than purple, okay? So these are nanometers. We always give visible wavelengths in nanometers. So something like 300 nanometers or less would be UV. Above 750 or so would be infrared. Okay? UV itself is broken down into, sometimes it's called short wave or long wave. Sometimes it's called UVA, I'll put it UVB. Those are just segments of the ultraviolet spectrum. Okay? I learned this quick way of dealing with UV from somebody, I've never forgot it, that UVA cause aging in the skin, UVB cause burning. So UVB is what gives you a sunburn, but UVA is what causes skin to age. And both of them cause cancer. Okay? But this picture, this kind of awful picture of this guy is so striking because look at the two sides of his face. This guy was a truck driver for his entire life. Okay? He always drove with the window up. Okay? So that's not a problem. The window blocks UVB rays. Okay? So you don't get a sunburn through light coming through a window. Windows do not block UVA. Okay? So an entire career worth of driving with the sun on one side of his face coming through the window. Look at the difference in the aging of his skin from one side to another. Isn't that amazing? So make sure most sunscreens now have both protection for UVA and UVB, but they didn't always used to, and some of the cheap ones do not. Okay? But even so, both of them cause skin cancer. Okay? Tanning beds are even worse because it's more concentrated. Okay? There is no safe form of ultraviolet radiation towards your skin. So UV rays have just the right amount of energy to begin to damage your skin cells. Okay? That's what a sunburn is. It's direct damage to your skin cells from the energy provided by the sun. Okay? So just the right amount of energy to start damaging skin cells, and then over time, they start screwing with the DNA in the skin cells, which is what causes cancer. So fun stuff to be talking about, right? So we're continuing on more and more energy, right? Increasing energy. Okay. Specifically, these ones, UV, X-rays, and gamma, those are called ionizing radiation. Which means now we're starting to have enough energy to remove electrons from atoms. So your oxygen atoms and stuff like that, if you start removing electrons from them, they start to become ions. And free ions, you've heard of free radicals, right? That's something that's short by one electron. And free radicals, they go all along, they cause all kinds of damage, right? A source of cancer. That's one of the ways that skin cancer is caused. But anything with sufficient energy to start forming ions, that's ionizing radiation, that's when it becomes harmful. Okay? So ionizing radiation, harmful. Let's just say that. The way that our goggles are sanitized between lab sections is with a UV light that has such ionizing radiation that it's able to kill any viruses or bacteria or fungi or anything else that's growing in there or alive. So, all right. So UV, X-ray. X-ray has more energy than UV. Okay? So it on a per wave basis, it's more harmful than UV. Not an issue if you're just getting X-rays of your arm or something like that. That's just for a fraction of a second. And even if you get lots of X-rays of your arm, that's not an issue. But for the person that's operating the X-ray, as I'm sure some of you will be at some point, it's a really big deal because they're doing that hundreds of times a day through an entire career. So it's really important that they're properly protected from the X-rays. They're usually not even in the room anymore. Okay? You also need to be careful with CT scans. Okay? MRI is totally different, but CT scans are just lots and lots and lots of X-rays all at one time. So especially if it's on your head, your doctors are going to be careful about how many CT scans you're getting. Okay? The reason that's useful in medicine is that X-rays pass through soft tissue, but are absorbed by bone. Okay. Back when we talked about electrons, remember we talked about Rutherford with the gold foil and detecting the electrons coming out on the other side. Rutherford was also, that same guy was one of the first person to discover X-rays. And it was totally by accident. Certain elements emit X-rays through their radioactive decay. And he just by chance happened to have his hand in between a X-ray radioactive source and some film, right? Just photographic film. Photography was starting to get really big right around then. So X-rays will develop photographic film, sort of just like light will. But what happened, the X-rays made it through his soft tissue, they got blocked by the bone, so what he saw on this film was just outlines of his bones right there, and the famous quote was, it startled him. He saw a vision of his own death, because the only way you would see bones like that at that time would be if you were dead. So, but it just so happens that X-rays have just the right energy to make it through soft tissue, but they get absorbed by bone. So whenever you get an X-ray, there will be an X-ray source that'll be on some kind of arm that they swing around. And on the other side will either be a cartridge of film or a digital detector that's just looking for the ones that made it through. Okay? And it fills in it makes a different color, the ones that didn't make it through. So you can see how your bones are broken. All right, so now that we're at the other end of the spectrum, gamma rays, shortest wavelength, but highest energy. Okay. So we see gamma rays given off by radioactive decay, and by nuclear reactions. Okay. So the flash of a nuclear weapon will be an intense surge of gamma radiation that can be very, very harmful. Okay? That's different from nuclear fallout, which is just particles of things that are radioactive that settle to the ground as just like dust. Okay? But a flash of gamma radiation is just kind of an instant thing that's very harmful. And then anything that's radioactive will also give off some gamma radiation to it. Okay? I found this symbol. We're starting to see this symbol a little more on food sources. And I want to educate you a little bit about this. You might really get the creeps from the idea that food is irradiated, usually with gamma radiation. And you might think that that's a terrible, harmful thing. It's actually a really, really good thing. Gamma radiation, it's kind of an on-off thing. Okay? Gamma radiation, it's just like a form of light. So when they turn it off, it's gone. Okay? So what they'll do, they do it with hamburger sometimes now. They'll have it just going through conveyor belts, a source of gamma radiation inside of a chamber that irradiates it, totally zaps it. What that does is kills all of the bacteria in that food instantly. Okay? Gamma radiation is so powerful that anything that is alive, all of its processes are stopped because its DNA gets screwed up and all that stuff. Okay? So it does it. But then the gamma radiation is off. It comes out of there. There's no more gamma radiation. Okay? Gamma radiation is just like light. When you turn it off, it's gone. Okay? Nothing is left behind. So it'll take a good amount of education to get people to be accepting of this, that in no way is anything harmful being put into your food from that. And what it's doing is killing off bacteria and things that cause foodborne illness like that. So, so many people get sick from the what is it in hamburger? Is that salmonella? It's one of those bacteria in hamburger. But if you have irradiated hamburger, you really don't have to worry about it nearly as much. But it's going to be forever before this is widespread, just because there are a lot of people that don't understand that will not buy something that says it's irradiated. Okay? But now you all understand that that's totally a good thing, and it can keep you from getting a foodborne illness. So we just went through all of these. I told you a little something interesting about each of them. What I expect you to know for these is their order. No, oops. Yeah, let's just write it right here. Okay. So you don't need to memorize any numbers, but know sort of what order they go in. Okay. And then know the trends of energy and of wavelength. Okay. So if we were doing that, if you know just sort of what direction energy and wavelength went throughout that order, I could ask you a question like, what has higher energy, ultraviolet or infrared? What do you think? What has higher energy, ultraviolet or infrared? Yep. Energy is increasing, going this way. Okay. Low energy, high energy. Ultraviolet is higher in energy than infrared. Okay. What has a longer wavelength? X-rays or microwaves? Yeah, microwaves have longer wavelengths. If you ever are interested in something fun if you get kids that are sort of interested in sciencey kind of physics things, do a search for microwave wavelength. Because what you can do, you can have a plate of marshmallows that you put in the microwave. It can't be turning, so you have to take out the turntable. But you put a plate of marshmallows in a microwave, little marshmallows. You can see that there's a pattern of certain ones of them getting heated up. And if you measure the distance between the ones that get heated up, you can actually calculate the wavelength of those microwaves. Right? Microwaves are just the right length. They're usually about like that. It usually fits 2 full wavelengths from the distance of the bottom of the turntable to the top inside of there, so it can get 2 full waves in before it hits your food there. So, yeah, that's a neat thing to do. You can calculate the speed of light from that. It turns out the speed of light is the relationship between wavelength and frequency. The frequency of your microwave will be printed on a little label inside the door. So it's kind of cool. Anybody have any questions about any of these? So again, you should know the order. You should know their trend. Have a general awareness of what kind of properties each of those ones have. Okay? All right.